The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
The next presentation was to be given by Neil Burke, but Neil was unable to attend this conference. He's overseas, and Mike Caldarone has stepped in to give the presentation on Neil's behalf. Michael Caldarone is Vice President of Engineering Services at Tourney Consulting Group in Kalamazoo, Michigan. He provides engineering services and manages the activities and professional development of the engineering staff there. He's a fellow of ACI and has nearly 30 years of experience in cement-based materials engineering, an emphasis on service life engineering of both new and existing structures. His book, High Strength Concrete, A Practical Guide, was published in 2009. We welcome Mike stepping in for Neil. Thank you.
Thank you. Good afternoon. I'm here to present the findings of some research that Dr. Burke had conducted on the use of zinc oxide in Portland cement-based mortars and concrete, but speaking for myself, I'm both pleased and honored to be here to speak on his behalf. So with Dr. Burke's presentation and a few little cheat sheets that I put together, hopefully you'll find this presentation interesting. Okay, basically, I'm going to talk a little bit about a background about zinc oxide, what zinc oxide is, some of the testing that was conducted at the corrosion inhibitor dosage levels of zinc oxide, testing that was used to check the feasibility of using zinc oxide as an admixture in mass concrete applications, some of the key findings of the work, and some future areas of interest. Okay, the work was conducted at Tourney Consulting Group in Kalamazoo, Michigan, and the work was sponsored by the International Zinc Association. Zinc oxide is a readily available material in excess of about 1.5 million, 1.6 million short tons per year. It's used in many different applications. It's a relatively safe material. It's found in pharmaceutical products, food products. There are industrial applications, and zinc oxide. A lot of people don't realize it, but zinc oxide has been used by the cement industry for a number of years. I think the cement industry would refer to it probably as a functional addition, mainly to control the setting characteristics of cements that have rapid setting characteristics, such as type K, shrinkage compensating cements. So it is a material that's it's not uncommon to the cement industry. The driving force behind the research is that zinc oxide is a powerfully effective corrosion inhibitor in very severely aggressive environments with respect to its ability to inhibit corrosion to metallic surfaces and things like that. So there's quite a bit of interest in evaluating the effectiveness of zinc oxide as a potential corrosion inhibitor for use in concrete applications. In addition to its used as a corrosion inhibitor, it does have the ability to increase the strength of the concrete, It's basically a white material. It's a pigment similar to titanium dioxide, for example, and it's available in powder form, granules, or in an aqueous solution. Principally, the work at Tourney was conducted to determine the fundamental properties associated with the dosage rates needed to provide corrosion inhibition properties. Mainly, we looked at setting time and strength. This was very much a screening type of project to check on the potential feasibility of using zinc oxide in concrete. Corrosion literature does report that when you use zinc oxide at about 1 to 3% by mass of cement, it can significantly improve corrosion resistance of the steel that's embedded in concrete in very aggressive environments. Tests have been done, and it is confirmed that it is a very powerful corrosion inhibitor. So dosage rates in this particular study, dosage rates up to 2% were used. Okay, 2 different zinc oxide materials were examined. Cadex 911, which has an average particle size of a little over 1/10 of a micron. That's basically about the order in magnitude of a particle of silica fume. Silica fume has an average particle size of about 1/10 of a micron. And Cadex 930, which is approximately 3 times that size, approximately 0.32 micron average particle size. To put things in perspective, 1/10 of a micron is about 1/150th the size of an average grain of like a type 1 or type 10 Portland cement. So we're talking about very minute materials. So some of the mixtures that we looked at contained calcium nitrite, a tried and true corrosion inhibitor that's been used in the concrete industry for a number of years. The reason why the calcium nitrite was included in some of the mixtures is because not only is it a corrosion inhibitor, but calcium nitrite is a very effective accelerator. And it can potentially offer additional corrosion protection. So the first thing that was done was some screening tests in mortars. Before actual concrete testing was done, some basic screening tests were done using mortars. There was a control mix. Okay, and then there were several mixtures that contained the zinc oxide. And again, 1 to 2% zinc oxide would be, the initial work looked at dosage levels consistent with using the product as a corrosion inhibitor. Okay. You can see that, and the mixtures, the mortar mixtures that had the footnote 1, that was with the Cadex 930, the coarser product of the two. And this one and this one right here use the Cadex 911, the finer product. But basically, the introduction of 2% zinc oxide of the 930 coarser product did increase the flow capabilities of the mortar mixture. Flow with the inclusion of the finer zinc oxide, the Cadex 911, was less than the control. Okay, and at a 1% zinc oxide content, the flow was not quite what it was with the control. And with the mixture that had 1% calcium nitrite in it, it had a similar flow. But the thing that really come away from this from this data is really to look on the right there at the set times. As you can see here, zinc oxide is a very powerful retarder of Portland cement. The set time test with control, fairly common. Initial and final set times about 3.5 hours, a little over 5 hours. Quite common for mixture, a mortar mixture produced at about a 0.59 water to cement ratio. And the same thing with the calcium nitrite. Calcium nitrite, as I indicated earlier, is an accelerator, and it did accelerate the system a little bit and came in a little faster than the control. But you can see with the inclusion of the zinc oxide at 1 and 2%, the set time tests were halted basically at the end of the day. So all we know is that the time to initial set and the time to final set with the zinc oxide was in excess of 9 hours. So some repeated mortar testing was conducted with combinations of zinc oxide, calcium nitrite, basically the same design as I'd talked about in the previous slide. This time we looked at 0.5% and 1% zinc oxide with 2% calcium nitrite addition. Some of the results that we saw was that the flow was reduced, and that all the mixtures that had zinc oxide had time to final set of over 12.5 hours. So again, we saw a very notable amount of retarding imparted by the zinc oxide. So, additional mixtures produced at a lower water to cement ratio with 1% zinc oxide and 2% calcium nitrite with a polycarboxylate super plasticizer for workability. We saw very high setting times, over 22 hours. Compared to the control and the calcium nitrite mixtures that had set times under 4 hours, time to final set. As far as the concrete testing is concerned, concrete testing was conducted with concrete produced at a 0.4 water to cement ratio. In the case of this series of concrete tests, the zinc oxide was added as a delayed addition 1 hour after the mixing, and the whole purpose of doing that was to see if we can get some cement reactions initiated to get them started. A lot of things happen when you mix Portland cement and water, and a tremendous number of things can happen the first hour. So the purpose was to try and get the cement reaction started, introduce the zinc oxide into the system, and see what happens from that point on. And one mixture with 2% calcium nitrite was added with the initial mixing. So basically, again, what we saw, there's 3 different mixtures here. The control mix was produced at about a 3-inch slump, 75 millimeters. Measured after 9 minutes. After 1 hour, the slump was not measurable. It had lost all of its workability and plasticity. In the case of the mix made with a 0.5% zinc oxide, again as a delayed addition, the slump was about 4 inches after 9 minutes, and then after an hour, it was a little bit. It was about between a 4 to 5 inch slump, 65 millimeters. In the case of the mix that had 2% calcium nitrite plus the delayed addition, 0.5% zinc oxide, the slump was 85 millimeters after 9 minutes, and it was down to a little bit over 1 inch, 30 millimeters after 1 hour. But again, the thing to come away from this, the story the most powerful story that comes away from this work is, if you look on the right, you can see both the time to initial set and the time to final set was very, very long retardation. And it's not necessarily a bad thing, okay, as I will explain. So what were some of the conclusions that came out of the work? Well, you know, retardation is quite excessive, comes as no surprise based on seeing some of these numbers, okay. So in and of itself, as it is right now, using zinc oxide as a corrosion inhibitor in Portland cement concrete, or to use it as a whitening additive, is not feasible, okay, unless some smart researchers come up with a way to offset the retarding effects of the zinc oxide. As good of a corrosion inhibitor as it is, based on this research right now, there needs to be some way of formulating it to offset the effects of the retardation. Now, what are some of the positives that we can come away with using its strong retarding effects? There could be a potential use in mass concrete, post-tension grout mixtures, or concrete that has long haul times associated with it. There's two very important things that mass concrete should have. Okay? It should have, and I use the term retardation, but a term that I like to use better is really hydration control. Okay? When we use the term retardation, it sounds like we're focusing a lot on just the setting time of the concrete. But one of the benefits of concrete that has extended setting characteristics is that we're controlling the hydration reaction, okay, as it relates to strength and other properties of the concrete. So it is actually something that is very desirable to have in many different high-performance, high-quality concretes, such as high-strength concrete. The last thing that we want in a high-performance, high-strength mix would be for the hydration reaction to get out of control. Okay, we want to purposely control the hydration reaction. How do we typically do it as an industry these days? Well, through the use of conventional retarders. Okay. Years ago, all that we can do as an industry to slow down hydration was to do what? To cool the concrete. Okay. Years ago, and I'm going back 40, 50, 60 years and beyond, we didn't have chemical admixtures to slow down hydration, and so we had to physically cool the concrete with things like ice. Okay, but today we can control hydration chemically, okay, independent of the temperature of the concrete, and so hydration control is a very important attribute in many different concretes. Okay. So, looking at zinc oxide for use in mass concrete, I'll go into some of the concrete mixtures. We looked at both normal durability type of concretes and high-performance concretes, both with and without calcium nitrite. And this time, the dosage rates of the zinc oxide were kept under 0.5%, because we already know what type of retarding effect we get when we're above 0.5%. And so the mixes that were chosen for the actual adiabatic heat of hydration work was based on the best mixes that came out of the concrete screening. So this is a very busy slide, but just to try and navigate through it, and I wish the pointer was working a little bit better, but it does. I don't seem to be. There we go. Okay. If we look at the first three mixes, the cement content, and it was all these were produced with a Type 1 general purpose Portland cement. The cement content was held fixed, 600 pounds per cubic yard. 0.49, 0.49, 0.43 water to cement ratio. Okay, the first mix had no zinc oxide in it. The second one had 0.67% by weight of cement, and the third one had 0.46 by weight of total cementitious material, because it did have some silica fume in it, mix number 3. As you can see here, if you look all the way at the bottom, at the compressive strength, the mix number 3 that had the Portland cement and the silica fume had significantly higher compressive strength. Comparing mix number 1 and mix number 2, they were both produced at the same water to cement ratio, 0.49. The mix that had the zinc oxide in it did have significantly higher strength at 28 days. But again, as you can see here, if you look towards the bottom, the initial set and the final set were still quite, quite long. In the case of both mixes 2 and mixes 3, we're looking at over 44 hours and 34 hours to get to the point of final set. And very similar with mixes 7, 8, and 9, which contain a little bit more cement, slightly lower water to cement ratio, but basically the findings were very similar. In the case of higher performance mixes, produced at about a 0.35 to 0.36 water to cement ratio, basically we saw the same type of trend, very high, very long setting times associated with the use of the zinc oxide. And as you can see here, if you look at towards the bottom again, these series of concrete mixes were run at relatively high temperature concretes. We're looking at about 100-degree Fahrenheit concrete. So in spite of the high temperature of the mix, we still saw relatively high times to initial and final set. But it does demonstrate, too, that you can make hot concrete as long as you control the hydration reaction. You can still get glorious strength out of it. So based on that work, three mixes were selected for the adiabatic heat of hydration. And this is basically what we saw. The control mixture, mixture number 13, contained no zinc oxide. Mixture 14 had 0.23% zinc oxide. Mixture 15 had 0.38%. And the actual heat of hydration was about the same. Okay, which there's two things that you would want to look for in a mass concrete mixture. You would want to have a mixture that has, number one, slower setting properties so that you don't get any cold joints in a large mass pour, and the second thing being proportioning it with a set of materials that impart the lower total heat of hydration. In the case of this work, we did achieve the hydration control where we can reduce the possibility of getting cold joints in a large 1,000 or 2,000 plus cubic meter mass element, but the zinc oxide did not lower the heat of hydration. It basically just delayed the inevitable. Okay. So the key findings, zinc oxide is a very effective retarder. It appears to have a significant improvement over strength at normal water cement ratios. There was only a minor reduction, if any, of strength at lower water cement ratios. The delay in set for heat development basically indicated to us that it would not be suitable for use in mass concrete applications, but can be highly suitable in its ability to prevent cold joints in a mass pour. So here's some of the future areas of interest. One of the things about zinc oxide is that it is a non-organic product. Historically, retarders that we use in our industry today are organic-based, mainly sugars. Okay, it could be very effective in concrete placements where you have long hauls involved, or you want to keep the concrete asleep overnight, or where you have to pump like grout mixes long distances. This will just give you an example of what happens with conventional retarders when the fungicide wears off and bacteria attacks the organic retarder. This would not happen with zinc oxide. Okay, so that is a big plus with the use of zinc oxide because it is an insoluble inorganic material, and it is highly suitable for a situation like this where you've got a lonely ready-mix driver on a long desert-like road. Could be 1 or 2 hours away from the pour. So with that, I'd like to thank you very much.